time to go on our little Cohen's D tour. In this quick lesson, we are going to look at the differences between statistical and practical significance. We will quantify effect size using something called Cohen's D. We'll talk about Cohen's D versus statistical tests, and I'll show you briefly how to do Cohen's D in R. So let's get into it. The results were significant. This must be the most important thing ever, right? Well, again, statisticians are really not good at coming up with the names for things. We think significant means sufficiently great or important to be worthy of attention. When we say something is significant, like our significant other, they're super important and a big deal. This common definition can confuse what statistical significance means, though. Results can be statistically significant, but only have a teeny, tiny, negligible real-world effect. For example, this is made up. The results were statistically significant. There was a 0.02 increase in IQ when using a special shampoo. What? First of all, a 0.02 increase is negligible because the standard deviation is 15, the mean is 100, 0.02 is basically nothing. And sometimes these kind of results can be significant if you have a big enough sample size. So, but does that really mean anything? No. You gonna use that shampoo? I mean, maybe if it does good things for my hair. Statistical significance does not equate practical significance. Remember, hypothesis tests only tell us the probability that we see this particular outcome if the null hypothesis were true. With a large enough sample size, lots of negligible differences can actually become statistically significant. Practical differences are differences that are large enough to actually mean something in everyday life. So what we really want to know is how different are the two means? Not just are they statistically significantly different from each other, because as we've seen, that doesn't always mean that they're practically different from each other. So how do we quantify that practical significance? Effect size, Cohen's D. So this is Cohen's D. Cohen's D is an effect size measure used to indicate standardized differences between two means. So it's quantifying the difference between two means, but in a standardized scale. And you know how much I love my standardized scales. If we were to look at this, it looks pretty similar to maybe the t-test and z-test we've been doing. The only difference now is that we are not dividing by the standard error. We're just dividing by the standard deviation. So standard errors are for comparing means and sampling distributions. This is just comparing two means on a standardized metric. Now, when you calculate all this, you will get D, which is that effect size measure in standardized units. This might look very familiar from earlier too. This looks just like calculating a z-score, but instead of using one person's score, we're using a mean. But the outcome is still going to be a value in the standardized scale. So now that you know how to calculate Cohen's D, how do we interpret it? How do we know if it's big or small? So remember that this effect size is in standardized units, aka like standard deviation. So think back to our simple z distribution. So an effect size of 1, let's say, that means that the two means are a whole standard deviation apart, and that is quite large. And there are no hard cutoffs, but here are some conventions. That small effect size will be about 0.2, medium about 0.5, and anything larger than 0.8 is considered large. Think back to that freshman 15 example we did recently. We can calculate the effect size for that and actually see how different the two means are from each other. So here we have 13, that was the sample, 15, that known population we're testing against, divided by 4, the standard deviation, and we get negative 0.5. So what does that mean? That means that our UT sample that we calculated is half a standard deviation lower than the national average. So it's right here. Here's our 13, here's our 15, and this little space here is about half a standard deviation. It is half a standard deviation below the national average. You might be wondering, how is this different from the t-test we calculated for our freshman 15 example? Cohen's D is a standardized difference between two means. So we take mean number 1, mean number 2, subtract them, and then we're going to divide by that standard deviation to basically make it sort of into like a z-score, into a standardized metric that we can understand and interpret. When we are doing a t-test, we are comparing sampling distributions to test a hypothesis. Test statistics determine how likely these findings would be if the null hypothesis were true. This is why it takes into account variance and that sample size in the form of standard error. it does not determine that magnitude of difference between the two. Cohen's d does determine the magnitude of difference, but cannot determine the likelihood of seeing those findings. So even if you got a really big Cohen's d, your results might be statistically insignificant. Let's look at a few examples. How would you interpret the following? Take a moment, pause me, and give it a go. Let's start with the first one. We have T24, we have 24 degrees of freedom, 25 people in the study, and it was 2.45 with a p-value less than 0.05, meaning that they were statistically significant. But this effect size, d equals 0.15, is actually kind of small. It's not super strong. So statistically significant, but small effect size. We look at this one. We have t of 24, same thing, but now the t-statistic is 2.05 and the p-value is greater than 0.05. So the results were not statistically significant and it had a small effect size. So this next one, we have T4, which is 5 degrees, we had 5 people if we had 4 degrees of freedom. 2.45, p-value is greater than 0.05 because you would have a really high critical value if you only had 4 degrees of freedom. But our Cohen's d is 0.80. That's pretty big. And you might want to actually go and do that experiment or that study again because you had a really strong effect size. You just had a really small sample size. So you might have been underpowered, meaning that you created a type 2 error. Now this last one, we have t of 4 again. Now our t-statistic is 2.78, p less than 0.05, d is 0.80. So this time it is statistically significant and we have a large effect size. There is something interesting going on here. So how do we interpret Cohen's d again? In a one sample t-test, a Cohen's d value of positive 1 would suggest that your sample of people, that x bar that you calculate, that sample mean, are a whole standard deviation above the average population. We may not be familiar with a certain scale and whether or not a difference of 10 points means anything, but standard units are helpful because we are familiar with them and we know what they imply. If I said a Cohen's d was 1.5, we would know there was a big difference between the two sample means. If instead I said a Cohen's d was about 0.06, you'd know there was little practical difference between the two means. So here are two different examples. One where Cohen's d would be close to 0. Can't really tell, but there's actually two distributions here, but they're pretty much right on top of each other. There is no difference between the two means. And if there is, it's very negligible. And over here would be an example of maybe a full standard deviation apart. So Cohen's d would be equal to about 1. And notice how the curves are further apart from each other because the means are different from each other. All right, now that we know about hypothesis testing and how to interpret Cohen's d, we can finally move on to comparing more than just one group to some known mean. Next up, independent samples t-tests. I'll see you there. Cohen's d in R. If you are doing statistical analysis in R, there are different ways to get effect size measures such as Cohen's d, and there are a lot of packages out there too to help you do it. But if you wanted to calculate a very simple one, this is how you would do it by telling R the sample mean, population mean, standard deviation, and we would just put it into our easy little formula, sample mean minus population mean divided by standard deviation, and you get Cohen's d.